Right now, an ancient traveler races through our solar system at over 200,000 kilometers per hour. Billions of years of journeying through the galaxy brought it here, and in less than 2 weeks, this object will reach its closest point to Earth before vanishing forever. 3I Atlas carries a designation that marks it as only the third confirmed interstellar visitor ever observed by humanity. Every other comet, asteroid, moon, and planet in our cosmic neighborhood belongs here. But this object formed around another star in another planetary system under conditions we can only imagine. Incomprehensible distances across the Milky Way separate its birthplace from ours, and now its trajectory will bring it to within 269 million kilometers of Earth on December 19th, 2025. That distance equals 1.8 astronomical units, almost twice the gap between Earth and the Sunday. No threat exists at that range, yet our most powerful telescopes can study it in unprecedented detail, close enough to extract secrets about worlds we will never visit and stars we will never see. If you're new to this channel, subscribing and leaving a like helps others find these deep dives into the cosmos. Settling in for the evening means adjusting your volume and getting comfortable, because we have a story worth exploring together. Everything about 3I Atlas seems strange, and that strangeness defines its central mystery. Composition, unlike any comet we've studied in our own solar system, a peculiar brightness pattern pulsing every 16 hours. An unusual ratio of certain metals that has puzzled researchers, ancient origins suggesting it carries information about a time in galactic history that predates everything we know. NASA marshaled an unprecedented fleet of spacecraft to observe it, including the Hubble Space Telescope, the James Webb Space Telescope, missions orbiting Mars, probes heading to Jupiter, and spacecraft designed to study entirely different targets that were redirected to capture data on this visitor. More than a dozen NASA assets alone have trained their instruments on 3I Atlas, and European and Chinese spacecraft joined the effort as well. Opportunities like this come along almost never, which explains the level of attention. Before 2017, no confirmed interstellar object had ever been detected passing through our solar system. Oumuamua appeared that year and disappeared within weeks, leaving more questions than answers. Borisov showed up in 2019 and behaved more like a conventional comet, but it departed before a thorough study could happen. 3I Atlas arrived in July 2025, and the scientific community had months to prepare, which meant every major telescope in the world started watching. What we've learned so far, challenges, assumptions about what exists between the stars, and what we might learn in the coming days as the comet reaches its closest approach, could reshape our understanding of how planetary systems form and evolve throughout the galaxy. Tonight, we trace the entire journey of 3I Atlas, from detection by a survey telescope in Chile, through passage past Mars and swing around the Sun, to its upcoming rendezvous with Earth's neighborhood. Hard science, genuine mysteries, and the controversial claims surrounding this object since discovery all deserve examination. By the end, you'll understand not just what 3I Atlas represents, but what it carries. A message in a bottle from another world, written in the language of ice and rock and chemistry, waiting for us to decode it. July 1st, 2025 brought a routine night for astronomers at the Asteroid Terrestrial Impact Last Alert System, known as ATLAS, operating from their telescope in Rio Hurtado, Chile. NASA funds ATLAS to detect objects that might pose a threat to Earth, asteroids, and comets that could potentially impact our planet with little warning. Thousands of faint points of light appear in the survey each night, most of them well-known objects following predictable orbits. One point of light that night matched no known trajectory. approximately 410 million miles from the Sun, placed the object well within Jupiter's orbit at the time of discovery. Magnitude 18 made it a tiny speck, roughly 100,000 times fainter than the dimmest stars visible to the naked eye. What immediately drew attention was the speed, 61 kilometers per second, relative to the Sun, which translates to about 137,000 miles per hour, or 221,000 kilometers per hour. Objects bound to our solar system follow elliptical orbits that obey certain velocity limits at various distances. And this object moved too fast to fit those constraints. Tracing its trajectory backward revealed an origin clearly outside our solar system, arriving from the direction of the constellation Sagittarius near the galactic center. Within days, the International Astronomical Union assigned the designation 3I Atlas, with the 3I indicating the third known interstellar object after 1I, Oumuamua in 2017, and 2I Borisov in 2019, and the Atlas portion crediting the survey team that found it. And that's when the early data got interesting. Archival observations revealed that 3I Atlas had actually appeared in images before its official discovery. NASA's Transiting Exoplanet Survey satellite, TESS, observed the region of sky containing the comet between May 7th and June 3rd, 2025. Serendipitous imaging during science validation observations from June 21st to July 3rd came from the newly commissioned Vera Rubin Observatory in Chile as well. Pre-discovery observations revealed something significant. The comet showed brightness and activity even when it sat roughly 6.4 astronomical units from the Sun, far beyond Jupiter's orbit. At that distance, most comets remain dormant because the Sun's heat lacks the strength to vaporize water ice. Activity at such range suggested behavior driven by something other than water, something more volatile that sublimates at much lower temperatures. Our first hint that this visitor carried a different chemical recipe emerged right there. Understanding the path of 3I Atlas through our solar system helps explain both the observational challenges and the scientific opportunities it presents. A hyperbolic orbit means the comet follows an open curve rather than a closed ellipse. Every planet, asteroid, and comet belonging to our solar system travels along a path that eventually loops back on itself, gravitationally bound to the Sunday. 3I Atlas lacks that bond, entering from interstellar space, swinging past the Sun, and then departing never to return, describes its path like a slingshot trajectory, a single pass through our cosmic neighborhood before continuing its journey through the galaxy. October 3rd, 2025 marked the closest approach to Mars, with the comet passing at approximately 29 million kilometers, or 0.19 astronomical units. European Space Agency spacecraft orbiting Mars gained their closest view of the object, closer than any Earth-based observation could achieve. Perihelion came next. The point of closest approach to the Sunday, October 29th, 2025, brought the comet to just 1.36 astronomical units from our star, placing it between the orbits of Earth and Mars. Solar gravity accelerated it to approximately 153,000 miles per hour, or 246,000 kilometers per hour during this passage. After perihelion, 3I Atlas passed Venus on November 3rd at about 97 million kilometers, and now it heads outward toward closest approach to Earth on December 19th, 2025. At that point, 1.798 astronomical units will separate the comet from our planet, roughly 269 million kilometers, or 167 million miles. Almost twice the distance between Earth and the Sun provides perspective on that number. NASA stated it explicitly. No danger to Earth exists from this comet, and it will pass safely before continuing on its way. One more significant encounter awaits in our solar system after Earth. March 16th, 2026 will bring a pass approximately 53.6 million kilometers from Jupiter, about 0.36 astronomical units. Massive Jovian gravity will influence the trajectory, though the comet moves so fast that even the largest planet cannot capture it. After that encounter, 3I Atlas will accelerate out of the inner solar system at the same speed it entered, roughly 137,000 miles per hour, and vanish into interstellar space. We will never see it again, which makes this our one chance. Months of observations from the most powerful telescopes available have revealed what 3I Atlas actually consists of. Determining dimensions of an interstellar object presents surprising difficulty because what we observe is not the solid nucleus directly, but the bright coma, the cloud of gas and dust surrounding it as ices vaporize. Hubble Space Telescope observations provided the best constraints, indicating a nucleus somewhere between 440 meters and 5.6 kilometers in diameter, with the most likely size falling below 1 kilometer. Early media reports sometimes describe 3I Atlas as potentially 7 or even 15 miles wide, but subsequent observations refined those estimates downward significantly. Current scientific consensus suggests an object roughly comparable to a small comet nucleus by solar system standards, which provides important context. Activity characterizes this comet unquestionably, meaning it has an icy surface that vaporizes as it absorbs solar energy, producing the characteristic coma and tail we associate with comets. Hubble images from July 2025 revealed a teardrop-shaped cocoon of dust surrounding the nucleus. More recent observations from November 30th, 2025 showed a bright central coma approximately 40,000 kilometers in diameter, with an extension stretching about 60,000 kilometers toward the sunday. Consider those numbers for a moment. The dusty envelope surrounding this object spans roughly 3 times Earth's diameter, and the outgassing structures extend across distances comparable to the Earth-Moon separation, all emanating from a nucleus that might fit within the footprint of some mountains. Spectroscopy, the analysis of light broken into component wavelengths, revealed the most telling information. James Webb Space Telescope observations on August 6, 2025 detected something that caught attention immediately: unusual richness in carbon dioxide. The carbon dioxide to water ratio measured at approximately 7.6, among the highest ever recorded for any comet. Comets in our solar system typically show much higher water content relative to carbon dioxide, but 3I Atlas releases carbon dioxide at about 129 kilograms per second, compared to only 6.6 kilograms per second of water. Composition tells us something about origins. The balance of volatiles in a comet reflects the conditions under which it formed, the temperature, pressure, and chemistry of its birth environment. Extreme carbon dioxide enrichment in 3I Atlas suggests formation conditions quite different from typical comets in our Oort cloud. Another compositional puzzle emerged from very large telescope observations that detected atomic nickel in the comet's gas emissions. Not unusual by itself, but iron appeared notably weak or absent. Most comets show nickel and iron together in roughly equal proportions, released from organometallic compounds that vaporize at relatively low temperatures. The unusual nickel to iron ratio has puzzled researchers, with some suggesting different parent molecules or chemical processing during the comet's long interstellar journey might explain it. One of the most intriguing behaviors observed in 3I Atlas deserves particular attention: its periodic brightness variation. Careful monitoring revealed brightness fluctuating on a cycle of approximately 16.16 hours, give or take about 36 seconds. A peer-reviewed paper confirmed this pattern, which represents the rotation period of the nucleus. As the comet tumbles through space, different faces periodically turn toward the sun, and active regions on the surface contribute varying amounts of outgassing depending on their orientation. The scientific explanation runs straightforward. An irregularly shaped nucleus with jets of gas and dust that become more active when facing the sun directly. Nucleus rotation over roughly 16 hours cycles these jets through periods of enhanced and reduced activity, creating the observed brightness variations. What makes this noteworthy comes from comparison with the previous interstellar object. Oumuamua displayed dramatic brightness variations in 2017, suggesting an elongated, tumbling shape, perhaps cigar-like or pancake-like. Variations in 3I Atlas appear more modest, with an amplitude of about 0.3 magnitudes, indicating a more conventional rotating body with localized active regions. 3I Atlas behaves much more like the comets familiar to us in our own solar system, just carrying a different chemical recipe. Let me consolidate what we've established so far. 3I Atlas arrived as an interstellar comet discovered on July 1st, 2025 by the Atlas Survey in Chile. Third, confirmed object from outside our solar system traveling on a hyperbolic trajectory that will take it past Earth on December 19th at a safe distance of 269 million kilometers. A nucleus likely smaller than a kilometer in diameter sits surrounded by an extensive coma of gas and dust. Carbon dioxide dominates its composition rather than water, setting it apart from typical solar system comets. Rotation occurs approximately every 16 hours, producing periodic brightness variations as active regions cycle toward and away from the sunday. That foundation established, we can go deeper. The most remarkable aspect of 3I Atlas involves not composition, but age. Astronomers analyze velocity through the galaxy to understand a comet's age. When 3I Atlas arrived in our solar system, it moved with specific velocity components in different directions relative to the galactic center. These velocities decompose into radial motion toward or away from the center, transverse motion around the galaxy, and vertical motion above or below the galactic plane. Vertical component proves particularly telling. 3I Atlas shows relatively high vertical velocity compared to nearby stars and other interstellar objects, suggesting it follows a tilted orbit around the Milky Way. Astronomers call this the thick disk population, a region of the galaxy dominated by older stars with lower concentrations of heavy elements. A study led by Matthew Hopkins, published in July 2025, estimated with 68% confidence that 3I Atlas falls between 7.6 and 14 billion years old. Independent analysis by Astor Taylor and Darrell Seligman estimated an age of 3 to 11 billion years. Both estimates broadly agree. This object almost certainly predates our solar system, which formed approximately 4.6 billion years ago. Consider what that timeline means. When 3I Atlas was ejected from whatever planetary system gave it birth, our sun did not exist. The cloud of gas and dust that would eventually collapse to form the solar system scattered across a region of space, undifferentiated and unremarkable. Dinosaurs remain hundreds of millions of years in the future. Life on Earth sat billions of years from emerging. This comet has traveled through the galaxy since before Earth existed to travel past. Extreme age provides context for unusual composition as well. During billions of years of interstellar wandering, galactic cosmic rays would have continuously bombarded the outer layers, high-energy particles that permeate interstellar space. A paper published in late October 2025 by Maggiolo and colleagues proposed that cosmic ray processing explains the extreme carbon dioxide enrichment. Radiation would have chemically altered the outer 15 to 20 meters of the comet's surface, converting some compounds while preserving others. Observed outgassing samples this processed material, not the pristine interior. The comet's surface functions as a record of its journey, a chemical diary written by the galaxy itself over billions of years. Tracing 3I Atlas back to its parent star proves impossible, unfortunately. Traveling for so long means experiencing gravitational influences from countless stars and nebulae along the way, scrambling the original trajectory beyond recovery. We know it arrived from somewhere in the direction of Sagittarius, but pinpointing the specific star that expelled it cannot be done. A letter with no return address describes it well. Scientific response to 3I Atlas represents perhaps the largest coordinated observation campaign ever conducted for a transient astronomical event. Hubble Space Telescope made first observations on July 21st, 2025, roughly 3 weeks after discovery. Those images revealed the teardrop-shaped coma in unprecedented detail and provided initial constraints on nucleus size. November brought additional Hubble observations to conduct ultraviolet spectroscopy, analyzing gas emission composition and measuring the sulfur to oxygen ratio. December 4th, 2025 saw a release of the most recent Hubble image showing the comet with its distinctive coma and extension toward the Sunday. James Webb Space Telescope targeted 3I Atlas on August 6, 2025 using its near-infrared spectrograph. That instrument uniquely detects molecular signatures of various ices and gases. And Webb confirmed the remarkable carbon dioxide dominance. Additional Webb observations scheduled for December 2025 will show how comet activity evolved following closest approach to the Sunday, and that's when the campaign became truly remarkable. NASA redirected spacecraft never designed for comet observation. Mars Reconnaissance Orbiter used its HiRISE camera to capture 3I Atlas from approximately 30 million kilometers, achieving the closest spacecraft view of the interstellar visitor. MAVEN, also orbiting Mars, detected hydrogen atoms surrounding the comet using its ultraviolet instrument. Perseverance rover on the Martian surface even paused geological exploration to photograph the comet, the first time any rover has ever imaged an interstellar object. NASA's Psyche spacecraft, en route to a metal-rich asteroid of the same name, observed 3I Atlas over 8 hours on September 8th and 9th, 2025, when about 53 million kilometers separated comet and spacecraft. Lucy mission, heading to the Trojan asteroids, spotted it from approximately 240 million miles away. China's Tianwen-1 Mars orbiter captured images of the nucleus in coma on October 3rd, marking the first time a Chinese spacecraft observed an interstellar object. European Space Agency contributed equally significant observations. ExoMars Trace Gas Orbiter and Mars Express both turned instruments toward 3I Atlas during closest approach to Mars in early October. Mars orbit provided viewing angles impossible to achieve from Earth, making those observations particularly valuable. ESA achieved something unprecedented with that data. Combining Mars-based observations with Earth-based telescope data, the Planetary Defense Team improved predictions of the comet's location by a factor of 10. First time ever that astrometric measurements from a spacecraft orbiting another planet were officially submitted and accepted into the Minor Planet Center database. Consider that achievement for a moment. Spacecraft at Mars triangulated the position of an object from another star system, refining trajectory knowledge with 10 times greater precision. Science and proof of concept for planetary defense converged in that accomplishment. If a genuinely threatening object ever approaches Earth, we now know spacecraft throughout the solar system can contribute to tracking it. Most recently, ESA's Jupiter Icy Moons Explorer, known as JUICE, captured images of 3I Atlas in early November. Farther from the comet than Mars orbiters were, JUICE observed the object just after perihelion, when activity increased. A partial navigation camera image released in early December showed an active comet with hints of two distinct tails, one trailing behind and one pointing more toward the sunday. Full scientific data from JUICE instruments won't arrive until February 2026 due to communication constraints, but early previews suggest significant activity. October 24th, 2025 brought another first when the Meerkat radio telescope in South Africa achieved the first radio detection of any interstellar object. The telescope detected hydroxyl absorption at specific radio frequencies OH molecules produce when solar ultraviolet radiation breaks down water vapor. Classic cometary activity confirmed, and our observational toolkit for studying future interstellar visitors expanded. Late November 2025 brought a preprint paper with a provocative new interpretation of 3I Atlas behavior. Researchers led by Trigo Rodriguez proposed that the comet might experience cryovolcanism, essentially ice volcano eruptions driven by internal chemistry. The proposed mechanism works like this. Solar heating during approach breached the threshold for carbon dioxide sublimation, the direct transition from solid to gas. That release enabled oxidizing liquids to flow into the comet's interior, where reaction with metallic grains of iron, nickel, and sulfides locked within pristine material occurred. Researchers conducted spectroscopic comparisons using primitive meteorites called carbonaceous chondrites, including samples NASA collected from Antarctica. One Antarctic sample contains material believed to originate from a trans-Neptunian object, a body from the outer reaches of our solar system. Analysis suggested 3I Atlas shares similarities with these ancient, unaltered remnants. Clarity about what this hypothesis means, and doesn't mean matters here. Cryovolcanism applied to a comet doesn't describe the same phenomenon as cryovolcanoes on moons like Enceladus or Triton. Scientists use it as an analogy for surface-driven pressure release events that might resemble volcanic activity. The hypothesis remains preliminary and has not yet been peer-reviewed. If subsequent observations support it, 3I Atlas would appear more complex than a simple dirty snowball, perhaps a geologically active world in miniature with internal processes driven by chemical reactions rather than heat from planetary interiors. Let me consolidate what this deep investigation covered. 3I Atlas appears between 7 and 14 billion years old, likely originating from the Milky Way's thick disk, a population of ancient stars. Cosmic ray bombardment over billions of years chemically processed its outer layers, potentially explaining the unusual carbon dioxide enrichment observed today. Scientific community mounted an unprecedented observation campaign involving Hubble and Webb space telescopes, multiple Mars orbiters, Perseverance rover, several deep space missions, Chinese spacecraft, and European instruments. ESA used Mars-based observations to improve trajectory predictions by a factor of 10, first time such data entered official asteroid and comet databases. Recent hypotheses suggest the comet might experience cryovolcanism-like activity with internal chemical reactions contributing to outgassing behavior. Meerkat radio detection confirmed classic cometary activity through hydroxyl emissions. An object simultaneously familiar and profoundly alien describes what we're dealing with. Comet behavior characterizes it, but formation under unknown conditions around an unknown star means it carries chemistry we're still working to understand. Something surrounding 3I Atlas, since discovery needs addressing. Speculation that it might not be natural at all. Harvard astrophysicist Avi Loeb argued publicly that 3I Atlas deserves consideration as a potentially technological object. His claims generated substantial media attention and dominated social media discussion. According to one analysis, approximately 40% of posts about 3I Atlas on social media invoked aliens or extraterrestrial technology. Loeb's arguments deserve fair presentation before examining scientific response. Several characteristics strike Loeb as anomalous. Comet trajectory aligns well with the ecliptic plane, the plane in which planets orbit, within about 5 degrees. Arrival direction falls within 9 degrees of the 1977. Wow. Signal, a famous radio signal of unknown origin. Nickel detection without corresponding iron appeared, and nickel appears in certain industrial alloys. More recently, Loeb suggested that coma extension toward the sun, sometimes called an anti-tail, might represent a swarm of unknown objects traveling with the comet. 30 to 40% probability of artificial origin represents Loeb's estimate, while he acknowledges the most likely outcome remains a completely natural object. Scientific response came unequivocally. November 19th, 2025 brought a NASA press conference specifically addressing the speculation. NASA officials stated directly, "This object is a comet. It looks and behaves like a comet, and all evidence points to it being a comet." Penn State astronomer Jason Wright published a detailed rebuttal on November 9th, 2025, addressing each claimed anomaly. Ecliptic alignment Wright characterized as a classic fallacy and misuse of probability theory, calculating odds after already knowing values rather than making predictions beforehand. Anti-tail features, Wright noted as understood phenomena for over 50 years. Viewing geometry and dust particle sizes create apparent extension toward the sun, and nothing makes them unique to 3I Atlas. Mass calculations underlying some conclusions Wright identified as erroneous, with precision claims roughly 1,000 times greater than data support. Nickel abundance, Wright explained as normal iron to nickel variation, with measurements made at unusual distances complicating direct comparison. Wright's summary landed bluntly. Zero planetary scientists give Avi's claims any credence. They're saying he's wrong because he's demonstrably wrong. Other scientists added important context. Non-gravitational acceleration that Loeb cited, the slight deviation from purely gravitational trajectory, matches expectations for asymmetrical outgassing as comets approach the Sunday. NASA confirmed observed perturbations appear small and compatible with standard cometary processes. Spectroscopy shows ordinary cometary materials: water, carbon dioxide, carbon monoxide, cyanogen, dust. No exotic alloys, no manufactured structures. Radio observations found hydroxyl emissions consistent with water vapor breakdown, not technological signals. Separate search found no artificial radio transmissions above 0.17 watts. A university study analyzing approximately 700,000 social media posts about 3I Atlas introduced the concept of alien of the gaps, the tendency to insert alien agency wherever natural explanations seem incomplete. That pattern accompanied each interstellar object discovery and will likely continue. What this controversy represents and doesn't represent needs clarity. Loeb holds credentials as a scientist, former chair of Harvard's astronomy department, and he frames his position as scientific open-mindedness rather than certainty. His critics argue his methodology doesn't meet standards required to support such extraordinary claims, which constitutes the problem. Scientific consensus stands unambiguous for our purposes tonight. 3I Atlas shows every characteristic of a natural comet, albeit one with unusual composition reflecting interstellar origin. Anomalies Loeb cites have mundane explanations. Extraordinary claims require extraordinary evidence, and that evidence has not materialized. Why speculation captures public imagination makes sense. The idea that something from another star system might be artificial touches, fundamental questions about our place in the universe, profoundly compelling territory. Compelling ideas and supported hypotheses differ, and data points firmly toward a natural object. Stepping back from 3I Atlas reveals what interstellar objects as a class represent for astronomy. Before 2017, no confirmed detections of objects from other star systems passing through our own existed theory predicted their existence because processes forming planets involve messy affairs with countless small bodies ejected into interstellar space during gravitational interactions of forming systems. Models predicted the galaxy should contain such wanderers, perhaps one passing through the inner solar system every few years. Theory and observation differ. Oumuamua's detection in 2017 transformed interstellar objects from theoretical predictions to confirmed reality. Borisov in 2019 added a second data point. 3I Atlas provides a third, and each teaches something new. Oumuamua presented strangeness, a highly elongated object showing non-gravitational acceleration without visible outgassing. Nature remains debated, with some astronomers believing it was a comet whose outgassing fell too faint for detection. Others propose more exotic explanations, including hydrogen ice or Loeb's technological hypothesis. Borisov looked much more like a conventional comet, by contrast, with visible coma and tail and composition broadly similar to solar system objects. Interstellar comets might not differ so much from our own, that discovery suggested. 3I Atlas falls between the two. Clearly, comet-like behavior with robust activity and measurable outgassing characterizes it, but composition stands distinct, with carbon dioxide domination, unlike typical solar system comets. Extreme age suggests it samples a population of objects from a very different era in galactic history. Three objects together hint at diversity existing between the stars. Comets and asteroids drifting through interstellar space don't form a uniform population. They reflect varied conditions under which planetary systems form throughout the galaxy. Different temperatures, pressures, chemical environments, and timescales that shape them. Each interstellar object functions as a fragment of another world, a piece of physical evidence from a planetary system we cannot visit. Analyzing 3I Atlas composition means learning about chemistry of a protoplanetary disk that existed billions of years before Earth. Measuring outgassing rates means sampling material processed by conditions utterly foreign to our experience. One astronomer described interstellar objects as space capsules containing valuable information about the chemistry ongoing in another location of our galaxy. A practical dimension to studying 3I Atlas extends beyond pure science, planetary defense. Earth has taken asteroid and comet strikes throughout its history, sometimes with catastrophic consequences. The Chicxulub impact 66 million years ago triggered mass extinction that ended the dinosaurs. Smaller impacts occurred more recently, including the 1908 Tunguska event and 2013 Chelyabinsk airburst. Modern astronomy made tremendous progress cataloging potentially hazardous objects, asteroids and comets whose orbits bring them close to Earth. Interstellar objects represent a different challenge, arriving from random directions with high velocities, providing much less warning time than objects on predictable solar system orbits. 3. I-Atlas poses no threat, and that point deserves emphasis. At 1.8 astronomical units, closest approach falls 36 times beyond the threshold that would classify it as potentially hazardous. No danger exists. The observation campaign served as valuable rehearsal for planetary defense regardless. ESA explicitly framed Mars-based trajectory refinement as a test case, triangulating observations from multiple locations throughout the solar system, rapidly coordinating space and ground assets, processing and sharing data in near real time. All of these capabilities matter if genuine threat ever emerges. International Asteroid Warning Network launched an 8-week observing campaign for 3I-Atlas, running from late November 2025 through late January 2026. First planetary defense exercise, conducted with an interstellar object, with the goal of training observers worldwide in extracting accurate position measurements from images complicated by coma and tail structures. A harmless visitor sharpens skills that might one day prove critical. Perhaps the most poignant aspect of 3I-Atlas involves our inability to reach it. Scientists studied whether any existing spacecraft could intercept the comet. Southwest Research Institute validated that a proposed interstellar comet intercept mission could have reached 3I-Atlas if launched in time. That phrase, if launched in time, carries the key limitation. Post-discovery launches would require velocity changes of at least 24 kilometers per second, far beyond any available propulsion system. ESA's Comet Interceptor mission, designed to visit a pristine comet from the outer solar system, cannot redirect to 3I-Atlas. Launch comes in 2029, and even if ready now, the comet's trajectory doesn't permit interception. July 2024 departure would have been necessary a full year before discovery. Fundamental challenge of interstellar objects lies there. Appearing with little warning, moving through our system quickly, departing forever. Remote observation remains our only option for now. Studies demonstrate something important regardless. Intercept missions remain theoretically feasible. Earlier discovery, a spacecraft waiting in parking orbit, ready for redirection, faster propulsion systems, any of these would have enabled reaching 3I-Atlas. Technology gap sits narrow enough that closing it within our lifetimes remains possible. Future surveys like Vera Rubin Observatory will detect interstellar objects earlier and in greater numbers. Future missions might wait in deep space for such opportunities. Future propulsion technologies might enable rapid response that seems impossible today. 3I-Atlas reminds us both of current capabilities and current limitations. A glimpse of treasure passing just out of reach. Less than 2 weeks remain until December 19th, 2025, when 3I-Atlas reaches closest point to Earth at 269 million kilometers. Best remaining window for detailed observation opens now. James Webb Space Telescope has additional observations scheduled for December. Scientists hope to see how comet activity evolved since perihelion, whether outgassing rates changed, whether new features emerged, whether composition shows variation. Ground-based telescopes will continue monitoring through spring 2026. Current brightness around magnitude 10 to 11 makes the comet visible through medium-sized amateur telescopes under dark skies. December 12th will bring solar elongation greater than 90 degrees, making midnight observations possible. Full scientific data from ESA's JUICE spacecraft won't arrive until February 2026, delayed by need to use a smaller antenna while the spacecraft protects itself from the Sunday. Even partial previews showed an active, complex object with multiple tail structures. Long departure follows. Close approach to Jupiter in March 2026. Gradual fading through 2026 and beyond. Eventually, invisibility as 3I Atlas continues toward wherever the galaxy takes it next. Let me consolidate the scientific picture emerging from months of observation. 3I Atlas represents an interstellar comet, third confirmed visitor from beyond our solar system. Formation occurred billions of years ago, likely 7 to 14 billion years in the past, around an unknown star in the Milky Way's thick disk. Interstellar travel, ever since, with outer layers processed by cosmic ray bombardment into a chemical state, quite different from pristine interior material. Carbon dioxide dominates its composition, with one of the highest carbon dioxide to water ratios ever measured in any comet. Atomic nickel appears, but iron emissions run weak and imbalance still under investigation. Rotation occurs approximately every 16 hours, with active jets creating periodic brightness variations. Behavior consistent with natural comet appears in every measurable way. Non-gravitational acceleration matches expectations for asymmetric outgassing. Spectroscopy shows standard cometary molecules. Radio emissions reveal hydroxyl from water breakdown, not technological signals. NASA, ESA, and mainstream scientific community stand unanimous. This is a comet, unlike any comet studied before, not from mystery or inexplicability, but from formation in a different environment under different conditions at a different time. Strangeness reflects diversity. A galaxy filled with planetary systems differing in ways we're only beginning to appreciate. Let me close with something more personal, a reflection on what 3I Atlas means. Beyond data and instruments and trajectories, we live on a small planet orbiting an average star in an ordinary region of a spiral galaxy. For most of human history, no way existed to know whether anything lay beyond the lights in the sky. Even after understanding that other stars were suns, potentially with their own planets, no physical connection to those distant worlds existed. Interstellar objects changed that equation. Not just light from afar, not just spectra to analyze, not just theoretical predictions, but physical matter from other planetary systems, chunks of rock and ice that formed around other stars and traveled across the galaxy to reach us. Observing 3I Atlas means looking at material that once belonged to another world. This object, tumbling through the void at over 200,000 kilometers per hour, carries within its ice the chemical signatures of a protoplanetary disk that existed when the universe was young. Countless civilizations may have risen and fallen on worlds we'll never know during its journey. Distances dwarfing any human travel separate its path from ours, passing through regions of space that remain forever beyond our reach. Purely by chance, trajectory brought it close enough to a planet with technological civilization that we could study it. Measuring composition, plotting path, arguing about implications, turning most sophisticated instruments toward a speck of ancient ice, and extracting information that traveled across the galaxy to reach us, all became possible. That doesn't diminish significance. That expands connection. Through 3I Atlas, we link, however, tenuously to the broader galaxy, to planetary systems we cannot visit, to history predating our own existence. The comet carries no awareness of us. Ice and rock, following the laws of physics, indifferent to meaning we assign, describes what it actually consists of. We create meaning, ask questions, point telescopes at the sky, and wonder what exists out there. That wondering, that restless curiosity, driving us to study every passing visitor, expresses something essential about what we are 3-eye atlas will be gone soon. Journey continues, eventually passing out of our solar system and drifting through interstellar space until some future encounter with another star, perhaps another civilization, asking the same questions we asked tonight. Data remains. Observations will be analyzed for years, maybe decades. What we learn becomes part of humanity's collective understanding, another piece of the puzzle describing a universe far larger and stranger and more varied than we once imagined. If you've stayed with me this long, thank you. These deep dives work because people like you value substance over sensation, accuracy over hype, genuine wonder over manufactured mystery. Subscribing, sharing, or leaving a comment with your thoughts helps sustain this kind of content if you found it worthwhile. For now, the ancient visitor continues its approach. 12 days until closest passage. 12 days to watch, to learn, to marvel at what the galaxy sent our way. Clear skies and good night.